Okay, so now that we know about homotopy, we can do what I suggested that algebraic topology was all about. We can discover a group relevant to different topological spaces called the fundamental group. And we're going to try to get there by the end of this lecture, but the principles are all sort of established, right? We have now established a way of defining homotopic paths between, say, this path here, and well, we now know that how to define whether or not two paths are homotopic, right? If we can find a homotopy, this function h of s and t, where h0 of t is the first path and h1 of t is the last path. So we understand that, and I gave a hint in the last lecture about why a space may have paths that, as far as fixed endpoint homotopy goes, are not homotopic with one another, right? So any space that has sort of a hole in it, right? Clearly, if I have fixed endpoint homotopies that go around the left side of the hole, and then fixed endpoint homotopies that go around the right, and there's example of two different homotopic paths, or two paths that are not homotopic, right? And likewise, we discussed that you could have a path that goes around the hole like this, and that's not homotopic to either one of the black or the blue path. So with a simple hole in the space, you have an infinite collection of equivalence classes of homotopic paths, because we showed that a fixed endpoint homotopy, or the property of path gamma being homotopic to path phi, this is an equivalence relation, and ergo with an equivalence relation we know that we can now partition all possible paths into equivalence classes, and we presume that we do that. So we're going to talk now about equivalence classes of paths. Okay, but we're not quite ready. We don't have a group though, right? Nothing here is a group. What we've done is we've broken up the space into equivalence classes, but not into a group. So now we're going to do this. We're going to kind of create the group. So how do we do that? Well, we know that if we have a path between 2 points, we understand that I can now take another point, right? And I can create a path from the endpoint of the first curve to the second curve, and I can kind of create a brand new path. If this is gamma and this is phi, I can create a path lambda, which is the traversal of gamma first, followed by the traversal of phi. We might write that as phi after gamma, right, in some sense. And this I can create as a path by reparameterizing t, where t goes from 0 to 1 on gamma, and then it goes from 0 to 1 on phi. I can create an S that starts here at 0 and ends here at 1. So we can combine paths, but what's critical is that the end point of the first path and the beginning point of the second path have to be the same. And this caused us a bit of a problem as far as using this combination of paths to create some sort of group structure. Because, of course, if I'm going to talk about all the possible paths in a space, I can have two paths that are just unrelated. They don't have the same endpoints. So I can't combine, using what I just said, I can't combine these two paths. And to create a group structure, every element of the group has to be combinable with every other element of the group. So if I'm going to suggest like some sort of set of all possible paths, right? If that's my set that I want to turn into a group, well, if I take one path, gamma, and another path, phi, and that those two paths happen to have this kind of relationship, meaning they don't share any points in common, or they certainly don't share the endpoints or the beginning points in common, then I can't combine them, so I can't create a group. If I restricted it perhaps to just the paths that have the same beginning and end point, I suppose you could start thinking about it, but it just doesn't work, right? This creating a group out of all possible paths the way we've talked about it isn't going to work. So let's kind of go back to the beginning and let's look at these 2 points, gamma if the path is gamma, gamma 0, and gamma 1. What I'm going to do is I'm going to say gamma 1 and gamma 0 are the same point, right? So I'm going to make it so that gamma 0 equals gamma 1, and any path is basically a loop, right? So I pick this point P, and P equals gamma of 0, and it equals gamma of 1. And now I've got a loop. And the loop goes in a certain direction, right? Because it starts at 0 and say, it's going this way, and it goes through, say, 0.5 and 0.6 and 0.7, and finally it comes back at 1. So the loop has a definite direction of traversal. Well, this is good. This gives me something I can start thinking about, it turns out. Because the first thing I notice about this, although this was actually true of the paths as well, but all paths can be traversed in the reverse direction, right? I can traverse the path this way, and it's still a path, right? Because now I'm going to traverse gamma of 1 minus t, and then if I define s to equal 1 minus t, I can define a new path, call it gamma inverse of s. And that's a path, right? And it starts at 0 and it goes to 1, but it goes in the opposite direction. It goes this way. So that's important. That's important. So I've created this path that goes backwards. So let's put that on the shelf. All right, so now we'll talk about the constant path. We've kind of got this idea of an inverse path, and we got to be a little bit tricky here, right? I'm foreshadowing. I've called it the inverse path. Really, it's the backwards path, right? In order to be inverse, we're looking for something like A inverse acting on A equals the identity, and that's what we're shooting for, right? So I'm foreshadowing a little bit because these backwards paths are in fact going to be related to inversion, but we have a few steps to go. But all I've really shown is that it's a backwards path. There's nothing about it that's truly an inverse. Because remember, if I tried to do, say I did backwards gamma, well, I guess the way I'm saying this is the opposite, right? It's gamma backwards gamma. So I'd have a point P, and I do this gamma, and then I do then I guess I don't do that. Then I do backwards gamma, right? Yeah, I end up back at the point P, but during this thing, I've actually left P and I've actually returned to P. So leaving P and returning to P is different than what we want to talk about now, which is the constant path. And the constant path would be, say, the constant path, we call it I. I is a function of T, and it's a path, so T goes from 0 to 1, but it always equals P, right? It never changes. So the constant path looks like this. Well, we're dealing with 1 point P, so I'll keep it in the same spot on our little plane here, right? That's the constant path. It never leaves. So the constant path is definitely not ever going to be equal to the forward path followed by the backward path. That's just simply not the case. So there's a level, however, we do want the forward path times the backward path to equal the identity somehow. And the constant path really does feel like an identity object. So the question is how do we bind all this together and create a group out of it, right? We've got something that we feel like should be arguably an inverse. We've got something that feels like it arguably should be a constant, but we just don't. Meaning the group's identity element, right? We have something that feels like an identity, something that feels like an inverse, and we certainly know about concatenation of paths, right? We talked about that. So with loops, right? A concatenation of loops, right? Gamma and phi, right? Phi is a loop, and we know that gamma after phi is a concatenation of loop, and that's another loop, or another path. So we know that. What is it? Gamma phi. Oh boy, that's weird. We know that gamma phi is also a path, so we can take any two paths that have fixed endpoints at one point, right? Any loop. Well, instead of saying, we know that when I say loop, I mean a path where the endpoints are the same. It starts and ends at the same point, and that point doesn't move either. So we know that we can combine any two loops to get another loop. We have something that feels like an inverse and something that feels like an identity, but it clearly doesn't quite all bind together as a group. In particular, the problem is that our inverse operations don't really produce what we want to call the identity. All right. So how do we deal with this? Well, this is where we haven't mentioned yet the notion of homotopy, right? We haven't discussed how homotopy is going to help us. I'm back talking about paths again, right? I'm talking about paths, but I'm not talking about homotopic paths. And we remember that homotopic paths or homotopies form a equivalence relation, and every equivalence relation forms an equivalence class. And that is the magic sauce that allows us to create something really important called the fundamental group. All right, so now let's take a look at how we plan to do this. These are all these point P's, they're the same. I've got several different pictures to illustrate different paths that leave point P and circle this or deal with this annular region in the plane. I need this little annulus here, otherwise all paths are homologous to one another, or not homologous, homotopic to one another. So one kind of path or loop that can leave P, it can leave P, do a little orbit out there in the plane, and then come back to P. And the fact that it goes out and comes back over one little segment on the same line, that's fine. That's totally fine. You can go out and come back. You can have a loop that just goes out and comes back on a straight line. That counts as a loop. That's fine. So this is one type of loop that we can have at P. And what's important about this loop is that this loop is homotopic to the constant loop. So this loop, which I'll call that loop phi 0. Phi 0 is homotopic to the constant loop. Phi 0 is homotopic to the constant loop. And every loop out there that is homotopic to the constant loop is a member of the equivalence class of loops that are homotopic to the constant loop. And that equivalence class is written like this, brackets around I, where you put a representative of the equivalence class inside the brackets, and the best representative in this case is the constant loop. So all of these loops that are representative or that are homotopic to the constant loops get jammed into a set, and that set is this equivalence class. So this set contains phi 0 as I've written it. It also contains this version of phi 0. It contains that version of phi 0. It contains this version. All of those paths, all of those loops are in this set. Obviously a very, very big set. It's got all possible paths that are homotopic to the constant path. What it doesn't contain is it does not contain this path, because that path is not homotopic to the constant path. Okay? So this equivalence class is very well defined. Now the next equivalence class is represented by this loop. It goes out to the annulus, goes around the annulus once, and then it comes back, right? That equivalence class is also a set of all the loops that can be homotopically blended into this loop, like those two green ones there, or even some loop that goes wild out here, and then boop, but it goes around once. That will all be homotopic to phi 1, and as such, it is a member of the equivalence class of phi 1. So phi 1 is our representative loop. In this case, it's this particular loop. It's a representative, but it's only just one member of a vast equivalence class. Now, phi 1, it's worth a moment to talk about the equivalence class of phi 1 inverse, right? Phi 1 inverse would actually go out, and if phi 1 goes this way, phi 1 inverse would go around like that and then back. Notice that these are not homotopic to each other. Phi 1 inverse is not homotopic to phi 1. You cannot take a loop that goes around this annular region clockwise and homotopically, or find a homotopy between that loop and one that goes around the other way. So these are different equivalence classes. So you could, in fact, instead of calling it phi 1 inverse, you could call this phi negative 1, right? And that's an important idea. So phi negative 1 and phi 1 inverse are two ways of writing the same equivalence class. Now notice that it is possible to, if you with the phi 0, if phi 0 is clockwise, you can homotopically start adjusting this part so that you flip the direction, and the final curve of the homotopy is the exact same points as the initial curve of the homotopy, but it goes in the opposite direction. So in the case of the equivalence class of paths homotopic to the constant path, it is actually true that phi inverse, these two sets are in fact the same. But it is only true for the class of curves homotopic to the identity. All the rest, you have the equivalence class of the opposite path, of the backwards path, is not the same as the equivalence class of the path. Anyway, you can proceed as described before, right? I mean, or you can keep going, right? I can go around twice, and now I create the equivalence class of all curves that go around the loop twice. And then I can create the equivalence class of all loops that go around the curve 3 times. And obviously I can do this forever, and not only do I produce a infinite sequence of a countable infinity of equivalence classes that go on forever, but I also create all of their inverses, right? I create phi negative 1, I create phi negative 2, I create phi negative 3, okay? And then I create phi negative n, for example. I don't know why I have this phi 0 here, right? So right now you can see that just by adding this annulus into the plane, I've suddenly created an infinity of equivalence classes. Now, if that annulus wasn't there, then every loop would be in a single equivalence class, and every loop would be homotopic with the identity, right? So that one little annulus changes the number of equivalence classes we have from 1 to infinity, right? So that's kind of interesting. It's a small change in the set. Well, the word small is totally meaningless here, because obviously it's a huge change, right? Because if you measure the change as the number of equivalence classes of paths that start and end at P, it's it goes from 1 to infinity in one little move. So it's a big change, right? So a hole in a plane is like a big deal. Okay, so now the abstract part comes. This is the part that gives people kind of a lot of trouble. Each of these equivalence classes is a giant set of loops, yes. But forget about all that. Now let's just think of the equivalence class itself as a thing. It's just a thing. So it's a thing that we've defined as an equivalence class of all these loops, yes, but I want to just now think of just the equivalence class. Because if I think of the equivalence class, I'm basically thinking of paths that go around this thing once, paths that go around this thing twice, paths that go around this thing 3 times. Just by referring to the equivalence class, I don't have to refer to any specific path. I just need to know how many times it goes around the annulus, right? And then I realized, it's kind of interesting. If I can now create a set, right? I can create a set of all the equivalence classes, right? Because now I'm thinking of the equivalence classes as elements of this set, let's see, I'm on phi 3, phi n, So there's an infinite number of them. Oh, and I should be careful to indicate there's also, phi minus 1, right? Phi minus 2, right? Phi minus n, forever and ever and ever, right? So this is a big old set, but the elements of the set are equivalence classes. Okay, so this set here, this set of these equivalence classes is the set that's going to make up what we call the fundamental group. The fundamental group of our topological space X located at the point P, right? Because remember, we had to pick this point P, right? Turns out that's not going to matter much for the spaces we're working with, but the set X is this plane with a hole in it, and P is the one point we've chosen. And now I've created the set of all the equivalence classes that start and end at P and are homologous with each other, right? The equivalence relation is not homologous, homotopic. There's another important group in algebraic topology called the homology group, and that's not this. This is the homotopy. This is the fundamental group, and it has to do with all the equivalence relation of being homotopic to each other produced all of these equivalence classes, because the equivalence relation partitions the set. That's what an equivalence relation does. And so the equivalence relation partitioned the set into these equivalence classes, and that set is going to be called the fundamental group. Now, a group is always a set, right? It's always a set of elements, but it's a set of elements with a group operation, which I can put like as a little black dot, and it has to have an identity element, and every element must have an inverse, and it must be associative as well. So I have to define the multiplication operation of this group. So that's what we're going to do now, just to be very clear about it. All right, so let's have a look at how we can think about our plane with an annulus, and we're going to talk about the concatenation of two particular paths. So we'll start with blue. I want you to see blue leaving point P and going around the annulus, right? And then it comes back to point P. In fact, let me make it really exaggerated so you can see that it comes back to point P like that. And it's going to be traversed in this direction. So we know that the blue curve is an element of the equivalence class phi 1. So it's a member of phi 1. But now we can concatenate it with a green curve. And to say the green curve, so now the blue curve is left P, gone all the way around and come back. Now the next thing it does is it joins with a green curve that does the same thing, right? And it comes back. So the path that green curve is also an element of the same equivalence path. So the green curve and the blue curve are both the same equivalent class. So I'll call the blue curve gamma, and the green curve, well, let's see, not red. The blue curve I'll call gamma, and the green curve I'll call lambda, right? So now I'm interested in the curve gamma lambda, right? So gamma lambda is going to be this red curve, right? The red curve is going to, and I'm trying to overwrite this, right? But clearly the red, I'm not going to be so good at it, but the red curve goes around like that. So now with this red curve begins and ends at the point P, right? But you'll notice that this part of the curve here that goes through this way, because remember the red curve left on the blue and then comes through here. So this part of the curve here, this vertical piece, right? This piece right here, right? That part. That part is not, it's going through P, but it's not beginning or ending at P. So we can move that. Homotopically, we can move that. So ultimately, this red curve can, this piece of the red curve, let's see, how would I do this? Let's see, undo. So there's the red curve. I've taken it away. And let me just look at just this piece of the red curve, right? I take that piece of the red curve and I start to move it, right? And I start to move it like this. So now the red curve actually would look like this. It goes around, and then it goes, instead of going through the point, it goes like this, and then back to the final point, right? So so these parts of those little pieces, those intermediate parts, you can see it intermediately would make this turn, but now it's all the way over to here like that. And now I can keep this up, and you'll see that I can deform, ultimately I can deform this whole thing into a curve that essentially looks like something like this. It kind of leaves, goes around once, around twice, and sort of comes back, right? And eventually I can make it look like, this. I can make it look like a member of phi 2. So what's important about this is what I've shown is I've taken two members of the equivalence class phi 1, namely gamma and lambda, and I've created a member of phi 2 through concatenation. And that will always hold, right? So the idea is I have gamma followed by lambda. Gamma followed by lambda has an equivalence class, and that equivalence class is phi 2, right? And what I'm learning is that so now my set G, right? My set G contains all of the equivalence classes out there, right? And what I'm learning is that I can take two elements of the set. I can take phi A and phi B, and the group operation I put in the middle with a little dot if I want to explicitly say I'm doing the group operation. I'm taking two elements of this thing I propose as a group, and I'm doing this group operation. Well, the group operation has to produce another element of the group. And what it's going to do is it's going to produce the equivalence class of phi A followed by phi B, which, based on this particular exemplar, right, the plane with the annulus, right, that's going to equal, in this particular circumstance, phi A plus B, right, phi A plus B. And that will hold for inverses as well, right, because if I had just reversed the green loop, so I had gone this way on the blue loop, but then I did this way on the green loop, I could have homotopically undone the blue loop. And that would have been phi 1 multiplied by phi minus 1, which would have been phi 1 plus phi minus 1, which would have been phi 0. And phi 0 is really another way of saying the identity, the paths that are homotopic to the constant path. And the reason this is different than the last circumstance, right, is because the loops are going in different directions now. Now the piece I left here, I left the blue path going in this direction, and then I suddenly turned around and I left the point going the other way. So now the piece that I can control is this part right here, right? That is the end of the blue path and the beginning of the green path. So if I homotopically move that to here, and then eventually to here, and eventually to here, and eventually to here, and eventually to here, you can see it's shrinking to 0, right? That's why the green path in this case is the inverse of the blue path. I change the arrow on the green path, right? If I change the arrow on the green path, let's see, where's the... So if this arrow here becomes this, right? Now the path that I'm working on is I leave P here, come back to P on blue, but then I continue this way, and the piece that I can homotopically move is this piece. And that piece, when I homotopically move it, you see, will still get trapped by the missing part in the center of the annulus, right? The annulus will still capture it. And that's why you end up with 2 orbits of the annulus. So changing the direction of the green path makes all the difference in the world. So the upshot of this is that the group operation in this example, and this is going to be true of any homotopy, right? The homotopy forms equivalence classes. The operation that you're working on is any representative of the first equivalence class. I can take any representative of the first equivalence class, any representative of the second, and I can form a representative of the resulting equivalence class. So this is telling me how to combine equivalence classes. And in this particular case, I actually can do it explicitly, right? This case of the single annulus in a plane, I can explicitly combine them by just adding the subscripts. Other sets that are more sophisticated, like the one we're going to talk about in one of the nearby lectures here, the next few lectures, it's not that easy to figure out what are all of these equivalence classes, right? This was really easy. It's just loops around an annulus. But this is stuff that you can do with very, very general sets, and studying and understanding how to find this set of equivalence classes is very difficult. But look what we got. We got our set. We have our operation. We now understand inverse, right? Every one has an inverse. The identity operation is kind of interesting, right? The identity operation would basically be I can take any path, even let's have an annulus. I can take any path out there, no matter what it is. It can go around a few times or not, and I can concatenate it with any path that is homotopically identical to the constant path. And obviously, I can take this path and shrink it to a point, and I end up with just the path I started with. So any member of the equivalence class of the identity with any other group element will always equal the group, the equivalence class you started with. So this is the identity, right? And this thing is all associative. You can convince yourself it's associative. So now we have defined the fundamental group. No matter what our set X is, we'll always have this. As long as we create these paths, as long as we can create paths can create loops. I can pick a point in the set. I can create the set of all the homotopically equivalent loops, and then I define the group operation as the equivalence class of homotopically equivalent loops operating on another equivalence class of homotopically equivalent loops will give me the equivalence class of the concatenated paths of any two elements of either of these two sets. So that's the group operation. And we know that there will always exist the homotopic set of all paths that are homotopic to an inverse path of a given path. So we know an inverse will always exist. And the constant path will define all the paths that are homotopic to the constant path will define our inverse. So the only thing remains is this trivial point that this whole thing depended on a point P, right? And clearly for this circumstance, I think you understand that if I swap P for Q, it wouldn't matter, right? And if I swap Q for R, it wouldn't matter. And it turns out this isn't generally true. As long as the underlying space X is path connected, right? As long as the underlying space X is path connected, if I create a loop at Q, I can then add to that loop at Q a path to R, P, that goes to P and back. And now I've got a loop at P, right? And likewise, if I have a loop at R, I could in principle add a path to P and back and then concatenate the loop. And now I have a loop at P. So any point in the plane that is path connected to the point P that we built this thing on will have the exact same group structure. In other words, the fundamental group really doesn't depend on what point you choose, as long as all the points are path connected to one another. And in all the sets we're going to study, they will be. So this P can kind of go away, and the fundamental group is actually only described by the underlying topological space. All right, and that's called the fundamental group. And look, the fundamental group of this space here, right? This space that we did here, where we created a plane with an annulus. Well, look, it's simply the rule. Right? The rule is simply the subscript A, the subscript B becomes the subscript A plus B. And that's true for positive and negative A, where minus A would represent the inverse to the phi minus A is the equivalence class of all loops that are backwards traversals of all the equivalent members of the equivalence class of phi A. So this whole thing, this process, is just adding numbers. And in fact, this group, pi 1 of this particular configuration, the set of points in a plane with a single annulus, it doesn't matter how big the annulus is, it can be as small as a single point. But as long as that's the set, then the fundamental group is isomorphic to the group of integers under addition, right? And that's what we say. We say the plane with an annulus has a fundamental group that is the integers under addition, right? All of this stuff about the equivalence classes kind of disappears because all isomorphic groups are mathematically identical. So we take the one that we're most familiar and convenient with, which is the integers. So I say that the fundamental group of the plane with a missing point or an annulus is the integers. And that's a huge thing, right? I just puncture the plane in one spot, and all of a sudden I go from the empty plane, whose fundamental group is simply the trivial group of just the identity, right? You know, there's only one member. There's only one member of the fundamental group for the plane R2, right? If I write it that way, that fundamental group is just the identity, and that's a totally trivial group. But I punch one little hole in it, and all of a sudden, the fundamental group becomes an infinite group, not even some weird finite group. It's an infinite group, and it's the integers, right? And so the fundamental group tells us something important about the underlying space. Whether or not there's a hole in it, right, is pretty clear from the fundamental group, whether or not there's a hole in this plane, at least. So that's an important, that's one of the, you can kind of start to see how these groups tell us information about the underlying set. Okay, so now we have done it. We've defined the fundamental group, and we've described it in terms of the plane. And I think that's all for now. In our next lecture, we will apply this concept to our Lie groups. So all this was just, a quick down and dirty rundown of understanding what the fundamental group is for a set. And the example we used was the punctured plane. There are other examples out there. I encourage you to look at them. I think the best other example is the torus, right? So let's consider the torus as a sort of a parting example. We won't go into deep mathematical detail here, but considering a point on the surface of the torus, we'll call that our base point P, and clearly we have paths that leave P and return to P that are homotopic to the constant path at P. And then we clearly have paths that leave P and return to P that are not homotopic to the constant path because they go around this sort of the donut side of the torus, I suppose. They go around this smaller radius of the torus. So those paths are not homotopic to the constant path. And just like orbits of the annulus, you can clearly go around that path multiple times, right? You can imagine very easily going let's see, I guess you would go down and around, and then around, and then around, and then around. So how many times is that? That would be, let's see, one time around, two times around, three times around, four times around. And then say on this fifth time around, you come up and then you go back to P. You come up and then you go back to P. Right? So there you're clearly, that would be equivalent to say something similar to what we were calling phi. Let's see, 1, 2, 3, 4, 5 maybe. So we have that, but we also have paths that leave P and do the more obvious thing, perhaps, which is to go around the torus this way, all the way around the big hole in the torus. And clearly that is not homotopic to the constant path, nor is it homotopic to this path, right? So the group structure of the torus, the fundamental group of the torus, is definitely more complicated than the punctured plane. And it turns out the fundamental group of the torus is Z direct product Z, where Z is the group of integers under addition. So, and that's because you can have a specified number of traversals of these smaller circles with a number of traversals with any arbitrary number of traversals of the larger torus. And so you can keep track. You can keep spiraling around like this, right? Each time you go around here, you pick up one extra loop around this way, while each time you go around here, you pick up an extra loop around the smaller radius of the torus. And so you need two numbers really to describe every element of the fundamental group. And so it's Z direct product Z is the way we characterize this. It's not so important to understand this notion of the direct product of the torus. There's ways of proving what the fundamental group is of the torus. We're not going to talk about them because we don't really need them for our work. But you do have to understand that the fundamental group of the torus is still based off of paths, but now we still have a fighting chance of seeing all the possible paths intuitively. Once you leave the torus, or equivalently, you can have double toruses. I mean, imagine a double torus. You could easily have paths that become very confusing very quickly, and keeping track of them could become very hard. But my point is that finding those groups tells us a lot of information. The fact that this group is the fundamental group of the torus is Z cross Z tells us a lot of information about the underlying structure, the global structure of the torus. And algebraic topology goes into that. Everything that you can learn that we know about is part of that subject. All right, so next time we are going to apply this idea to our study of SU2 and SO3, right? We left off with we had done the calculation explicitly of how to calculate SU2 and SO3 and the structure of its coordinates on a manifold, or we did its coordinate analysis of its coordinates, and we discovered the fact that we had these, in SO3 we had this antipodal identified points, and in SU2 we had all these points on a sphere identified. We're going to have a look at that, and we're going to see if we can figure out the fundamental group of these two groups. Because remember, SU2 and SO3, they're topological spaces, right? So if you go back to the beginning of this whole story, this all depends on paths in a topological space. Well, this we've been using a plane, right? Here we've been using a plane. I've been calling it an annulus. That's really not right. It's a plane with a hole punched out of it. I guess the whole plane is somehow an annulus because it has a hole punched out of it. I've been referring to the hole as though it was an annulus, but that's not right. I don't know why I said it that way. But here we played with a very simple geometric set that's pretty familiar from geometry. We're going to replace this plane with a hole in it with SU2 and SO3. And that is not something you can visualize. But we're going to try anyway, and we're going to learn what the fundamental group of those two objects are. And what we're going to discover is that the fundamental group of SU2 and SO3 are not the same. They are not the same. And the fundamental group is a topological invariant. So that means that SU2 and SO3, as similar as they are not homeomorphic to each other, and they're not the same group. Okay, so that's a little teaser for next time, and I'll see you next time.